Hello, welcome you all. We shall continue with another numerical appeared in the examination, and this is from July 2017. The problem you already have with you. We shall read it and then continue. At room temperature, the gap between bar A and bar B shown in figure question number 2b is 0.25 mm. The diagram is already with you, and I also have drawn for your sake, and intentionally I have shown this 0.25 mm as if it is quite big, because my lot of work is going to be in this region, therefore I have made it quite big. Okay, next. What are the stresses induced in the bars if the temperature rise is 35 degrees centigrade? The temperature rise is 35 degrees centigrade, therefore it is delta T. I don't know the room temperature and what is the final temperature, that also I don't know, but I know that delta T is 35 degrees centigrade. Given area of cross section of A, say we have some information. A is known. A is 1000 millimeter square. And then I know AB 800 millimeter square. What is the nature of the cross section? We don't know. It may be rectangular, square, doesn't matter. The cross sectional area is known to us. Then Young's modulus of elasticity EA is 2 into 10 raised to 5 Newton per millimeter square, and EB is 1 into 10 raised to 5. Okay, then alpha A, all these values I should have written and then started. That will save some time. 12 into 10 raised to minus 6 4 degrees Celsius, and alpha B is 23 into 10 raised to minus 6. 23 into 10 raised to minus 6, 4 degrees Celsius. This is all data that has been given. And LA, the length I have already written there, 400 mm and 300 mm. Okay, all these things are different. Okay, now what is asked? If the temperature changes so much, what stresses are induced? Why the stresses are induced? When there is increase in the temperature, you know that this bar will extend its length, and this bar also will extend its length, and the other side, this side it is rigid, it can't expand this side, it has to expand here only, and similarly the bar B also has to expand this side, and probably they touch each other, and that is why we are going to have stresses. If they don't touch each other, then we are not going to have any stresses. Okay, now let me start with what is called as, I shall calculate delta L. What is this delta L? The free expansion. The free expansion of bar A I shall calculate. What is that? How much? That is alpha A 12 into 10 raised to minus 6 into length A, that is 400 mm multiplied by delta T. This 35, this will give you what is delta L of A? 0.168. Okay. Similarly, let me complete this delta L of B, and then I shall come back there. Delta L of A is how much? 12 into. Then this is 23 into 10 raised to minus 6, and the length is only 300 and 35. 0.2215 millimeter. 2415 millimeter. Okay, now let me see here what happens. Okay, probably I may have to the same thing I shall. So probably for delta L A expansion. So let me assume that it comes up to here. So what is this? This is delta L of A. Okay. So now B also will expand here, but for the sake of understanding here, I shall assume that B has been shifted down, and I shall show the expansion of B slightly below, and it is 23, okay, 0.2415, slightly little less than this 0.25, and therefore the B will come up here. So as if B, if I take it here, I have shown, and this is what, and this length from here to here. How much is this? Delta L of B. Okay, this will come up to here, and this has come up to here. Okay, now there must be some this thing. Okay, this will get compressed, and I don't know whether this also will get compressed, or if I say compromise the solution is somewhere here, then this will expand and this thing. Okay, so now, so you have to imagine the forces that are acting on it. So first of all, let us arrive at what is the compromise position. Can the compromise position be somewhere here? Or can the compromise position be somewhere here? Okay, so let me see. So whether this can be the compromised position, I just want to try. So for that, this bar also has to expand. So that means I have to apply a force in this direction. And this has to be compressed, and therefore I have to apply the force in this direction. So the force towards right, the force towards right, and this can never be in equilibrium, this will never be, and therefore this cannot be, the compromised position cannot be here. I hope you have understood. The compromised position should be in such a way that the force which will expand or compress, whatever it is, they also must balance each other, or in other words, that also come to the equilibrium position. So therefore the compromised position is somewhere here. So for that, if this is the compromised this thing, then here this portion is compressed and this portion also is compressed. So both of them, say this is P is towards left and this P is towards right, and therefore they balance each other, and therefore the bar will remain in equilibrium state. And therefore what is this length? How much is this length? And how much is this length? Okay, so how much is this? This is equal to P into the length of which portion? Length of A, P into LA divided by AA into EA. And similarly, what is this length? This is P into LB into AB into EB. Okay, so now this is the compromised solution, and now I have to write out, make use of all these dimensions. From here to here, I know that it is 0.25. Okay, so then probably I shall go on doing that. Write down the equation. Okay, so can I have this portion or let it be? No problem. Okay, how do you write down? So here the same portion is here also, I have shown. Okay. Delta LA, if I start delta LA, I am here. Okay. Delta LA, delta L of A, that is nothing but this. then minus this, I shall subtract this question. So I start from here, I go up to delta LA, that means I am here. I am coming back to this question, and therefore I am subtracting it. Minus P LA divided by AA into EA. This is what? Okay, I start from here. Okay, ultimately I want to reach here. Okay, I start from here and go up here, and then I come back. I am here now. Okay, so in this question, now I want to go again here. I want to go again, that is in the backward direction. I want to go back, that is in the backward direction. So how much backwards you are going? Okay, again minus, how much is this distance from here to here? That is P, LB, AB, EB. I start from here, please understand, I start from here and went up to here. That is the first term. Then I went back, therefore it is in the minus direction. How much? That is here. Okay, I am here again the same thing, and again I am going back this much distance, that is nothing but PLB this thing. Then from here, then I go up here. So how much from here to here? That is plus delta L of B. Once again, so from here I want to reach this end. So this distance I know that it is 0.25. So I start from my journey in this direction. So from here I first go up to here. That is this. That is delta LA. Then I go back from here to here. That is why I am subtracting. How much? I am subtracting this much. So I am here now. Then again I go back in the reverse direction. So then how much? That is PLB. That is this much. Then from here I then reach to this, the end. Okay. So how much distance I have covered? This distance is equal to 0.25. Maybe you can remove this square bracket. There is no need of square bracket. Okay, what is delta LA? Delta LA is 0.168. 0.168. Okay, so I shall plug these two. Then I shall write delta LB. Delta LB is how much? Plus 0.2415. Okay, I am taking this term and I am also taking this term. And this 0.25, I shall send it to the left hand side. Minus 0.25. And these two terms I shall take it to the right hand side. That is P into bracket LA. LA is 400 mm divided by AA 1000 into EA. This is 2 into 10 raised to 5. Then plus, because both of them are minus, taking it to the other side. This is 300 divided by EA 800. AA and EB. EB is 1 into 10 raised to 5. You can simplify this and then find out what is called as P. P is so many newtons. And once you get P, then P divided by AA will give you what is the stress in the material A, and P divided by AB will give you what is the stress in this thing. And in one thing you understand here, both of them, the material A has been compressed, therefore A is subjected to compressive stress and B also is subjected to compressive stress.
P is
27.73 into 10 raised to 3. Okay, very simple now. Once you get this P, you can get easily sigma A and similarly sigma B. I hope you have understood and you will be able to calculate. What is the nature of stresses in both A and B? So the stress in A, it is compressive. Stress in B, again it is compressive. Both members are subjected to compressive stresses. Each member is pressing against each other and therefore both of them are subjected to compressive stress. I hope you understand that. Fine. So let me go to another problem. So this is quite simple and very similar to the ones which have been done already. Okay, this is from January 2015 and so now what it goes. So a compound bar is made up of a central steel plate. We don't have a pipe rod now. It is a pipe, it is a plate. So plate 50 millimeter wide and 10 millimeter thick. 50 millimeter wide and 10 millimeter thick. Okay, probably it is something like this. So you have a plate. Intentionally I shall show you as it is quite thick. Okay, when you look from the side view, either this way or this way. Okay, so I am more comfortable with third angle projection and therefore I shall draw it here. So this is 50 mm and this is 10 mm. Okay, come back. A compound bar is made up of a central steel plate. So this is made of steel plate 50 mm wide and 10 mm thick, to which copper plate 50 mm wide and 5 mm thick are connected rigidly on each side. So there is one plate here, this side, and another plate this side. What are the sizes of that? Look at this. So you have one plate. So width is 50 mm only and thickness is 5 millimeter. And similarly you have one more plate this side also, whose width is 50 mm and again thickness is 5. Okay, this is one plate and this is your second plate and this is another plate, third plate. You have plates like this. Okay, then the length of the compound bar at room temperature is 1000 millimeter. So this length at room temperature is 1000 millimeter. Okay, 1000 millimeter. If the temperature is raised by 100 degrees centigrade, delta T is 100 degrees centigrade. Okay. Determine the stresses in each material and the change in length of the compound bar. What will be the new length of the compound bar? Okay, this is copper and this also is copper. Okay, your alpha of copper, L of copper, L for all the things remain same. Young's modulus of both materials are given. Okay, so all that data you can write it down. I shall skip it. Okay, I shall go directly to what is called as delta L of copper. So this is nothing but alpha of copper. Okay, 18 into 10 raised to minus 6, 18 into 10 raised to minus 6 into length of the copper, it is 1000 millimeter into delta T. Delta T is 100 degrees Celsius. I shall find it out. This is 1.8 mm. So the copper plates, okay, assuming that the increase in length will take only one side, so that means this copper plate will go up to here. And it is not the only copper plate, you have this side also. One more copper plate and these are in one line. So this length is what is delta L of copper. Okay, now let me find out on the same lines what is delta L of steel. Okay, this is alpha of steel, 12 into 10 raised to minus 6, and the length is 1000 only, and the temperature rising 100 degrees Celsius. 1.2 mm. let me show that 1.2 mm probably, so up to here, and this length, this is delta L of steel. Okay, the copper plates come up to here, steel plate only up to here, assuming that the entire extension is only one side, assuming that this side is rigid. Okay, so now they will come to a compromise. So what may be the compromise? Somewhere here. This is the compromise position. For that, this steel plate must undergo extension. So it is subjected to a force P. So which makes it to move so much, increase its length so much. So what is this length? Value P into LST or LC divided by area of steel, Young's modulus of steel, EST. Okay, this plate and this plate is subjected to some force, and this plate also is subjected to some force. So what should be the force? They are identical plates, therefore they will have equal amount of force. This cannot be P and P. If this is P and P, then 2P will be the force towards left hand side, and P is the force towards right hand side. It won't remain in the equilibrium position, and therefore this must be P by 2 and this must be P by 2. So P by 2 and P by 2, the resultant together, that is P towards left and P towards right, which makes it to remain in the equilibrium state. And therefore, what is this length then? What is this length? This length is equal to this P. P is nothing but P by 2 into L. L is nothing but L only, that is 1000 millimeter, divided by area of copper, not the entire both plates, area of copper plate, one plate, area of copper one plate multiplied by ECU. Okay, that. Okay, now we have everything. You can write down the equation. Okay, I can start from here. Okay, so start from here and go up to here. From here to here. From here to here I shall go. How much is this? That is nothing but delta L ST. Delta L ST. What is the expansion? The free expansion of the steel from here to here. Then from here I go up to here. This length. That is nothing but plus P into L divided by AST into EST. So I started from here, this is the first one, then from here to here. Okay, then from here to here. From here to here, this length is same as this. Plus P by 2, that 2 is in the denominator, length divided by area of copper into E of copper. So I started from here, this is the first one, plus this, what is this from here to here? That is same as, that is equal to delta L of copper. Okay, substitute now, delta L ST, how much? It is 1.2 plus, okay, so P I shall take it common, P into bracket, and L also I can take it common, P into L, L is 1000 millimeter, P into L. This is 1 divided by area of steel. What is the area of steel? Steel is at the center, that is equal to 50 into 10. 50 millimeter width and 10 millimeter thickness. 50 into 10 into EST. What is EST? EST is 200 gigapascal, that is 2 into 10 raised to 5. 2 into 10 raised to 5 plus. Okay, again L has been taken outside. This is 1 divided by 2 times. What is the area of copper? Each plate. Okay, this is 50 into 5. 50 into 5 into E of copper. E of copper is 1 into 10 raised to 5. Okay, these terms have been taken into account. This is equal to delta L copper. delta L copper is 1.8. Simple. Take this 1 point to this side, simplify, and finally get what? Get what? Get P. Okay. Then P is so much Newton. Then what is sigma ST? Sigma ST is equal to so many Newton per millimeter square. What is the nature of stress in the steel? It is tensile. And what is stress in copper? This is equal to copper plate. Each plate is subjected to P by 2. Okay, P by 2 divided by this 50 into 5.
P is 20 kilonewton.
20 kilonewton. 20 into 3. Okay, 20 into 3 divided by 50 into 10. 40 Newton per millimeter square tensile. Okay, this is sigma copper in each plate. Please here, this plate and this plate. Okay, I take only one plate. The stress is load is P by 2. That is 20 into 10 raised to 3 divided by 2. That is nothing but 10 into 10 raised to 3 Newton divided by area of the plate. That is nothing but 50 into 5. So we calculate this, so many Newton per millimeter square, and this is compressive. 40. This also is 40 compressive. Okay. And you are asked one more thing. What is the change in the length of the compound bar? What is the final length? The final length is here. You see here. The final length is here. Okay. The initial length. And after the compromise, they have come up here. This is what is the extension. I want to know what is the extension of the compound bar. Okay, that is nothing but delta LSP from here to here plus this to this. That is nothing but this length. Delta LSP plus the change in length of the bar. Delta L of bar is equal to, you can see here, this is the final position. So from here to here, that is delta LSP. Everything is there in this diagram. This diagram is very important. Therefore, make this as neat as possible. Delta LSP plus from here to here, what is this length? That is nothing but plus PL divided by ASP. Yes. Okay, simplify this. This will give you what is delta L. That is nothing but the change in length of the compound bar. 1.4. Okay. So the problems are very similar almost. Okay. So maybe I shall spend one more session on this and choosing different kinds of problems, and I shall solve it. So right now, please practice. You can pick the problems on your own and then practice. If you have doubts, please ask me. I shall be very happy to answer your doubts. Thank you. Good day.